All right, so here we start out with a basic. Oh, by the way, this is vibrations, week 1 and video 3. We use models in vibrations to represent real things, and so here's the most basic of models. This is the force damped vibration model, as we mentioned in the previous video. Here's an external force that's based on time, so it fluctuates with time. We have some coordinates, so it's a single degree of freedom. We have mass. We have a stiffness that resists motion. It resists the X motion. And we have a C, or a damper here, that resists velocity. We will talk some more about this, but it's an interesting type of thing where if you take a damper, quite often a damper will be like a sort of a plunger type of thing in a housing along these lines right here. All right, so here's the leg of the damper, and they had little tiny holes in here, and there'll be some fluid inside. And when you push this, the fluid has to flow through the other side. It could even be pneumatic, so it could be, but it could be some kind of oil or what have you. And so the fact that it's that the faster you push, the larger the force is. So the force is a function of the velocity. So that's what happens here. So that's why we end up with the equation mx double dot plus c x dot plus k x, and for this, force is a function of time. So this is the equation of motion for this. And this could be represent all kinds of systems. We could use this very simple, complex thing to do things like car suspensions or machinery mounts. I wrote down drums, okay. Drums and percussion. Probably just in the simplest sense. Also sound like buildings during an earthquake. All right, so I've talked about the model. Let's see what we could do with the model right here. So we want to apply this to harmonic motion. And so this is like a piece of paper. What this is supposed to illustrate is a piece of paper that's being pulled in that direction and tracking with the motion of this mass as it's going up and down on a spring. And so this is occurring with respect to time, and here's the motion. And some of the definitions, here's the amplitude. We usually refer to amplitude as being 1/2 of the total amount of motion right in there. And we also have this right here is a tau is period. And one of the first things that we should recognize is that the frequency is 1 divided by tau, right? So if you want to know if you want to calculate the frequency in hertz, it's 1 divided by tau. And so the period is the time for one repeat, right? So you can just look at a spot, and when it goes back up here, this is where it repeats. Let's see, anything else I want to say about this? No, let's go back over. Let's go in there. All right, so here we're going to do the most basic of solutions. So this is diffie-qs. We're not going to get too crazy with the derivation here, but we do want to account for a legitimate question. So right here, this is the FBD. And this is, by the way, this is out of your dynamics book. So first off, we do the statics of this and find the sum of the forces. And what are they calling this? I guess they're calling it X. I don't like that, but there we go. And they're saying that positive is downwards, so we'll go ahead and stick with that, is equal to 0. So we take a look at this FBD and we go, okay, well, the weight is downwards, but the tension in the spring is going to be negative because it's going in the opposite direction, and here's your static deflection, right? So that's how much the spring has stretched with when we're at this weight. I'm going to leave it in this form because we might be able to see later on that guy right there is something that pops up. Now we go to dynamics and we have an FBD now in this case, and an IBD, or the inertial body diagram is what I refer to it. And we've moved the spring a little bit, right? So we've displaced it some. So that's this guy. That's that picture right there. Here's its maximum or minimum. Here's what it's going about. Here's its equilibrium spot, and that's the location where we went ahead and we did the statics. So we come over here and the FBD equals IBD, and we say the sum of the forces in the x direction equals mass times acceleration in the x direction. And once again, downwards is what we consider positive. And so we take a look over on the FBD side. We have the weight of the thing still right there, and we're going upward to K times the static deflection plus whatever deflection happens onto there. All right, so then it equals on the right-hand side the IBD, right? That's why we draw both diagrams. And we have mass times acceleration, but that acceleration can also be defined as x double dot. So when we get to distributing this out a little bit, we can go W minus K static deflection minus K times X equals mass times X double dot. And we note that right there is the same thing that we got up above, right? So here what we've just shown, we can bring this negative over to the side, and we go mx double dot plus kx equals 0. So this is the equation of motion, and this is just how we go about with an FBD getting it. So let's see what I have. Do I have it on the next page? No. What kind of things does this? All right, so here's where diffie-Qs really comes into play. What are the solutions to this? Well, let's change the form just a little bit and divide, well, not equal. So we go plus, and then go K over M X equals 0. And we ask ourselves, what kind of thing does this? Well, what kind of differential equation? This is a second order homogeneous differential equation. And it's linear, by the way. And we can put some brackets or some parentheses around that. And we can ask ourselves, what kind of thing does that? Now, so this is like a really important question as far as I'm concerned, because I took a lot of math. It was only when somebody asked this question, the differential equations asks the question, what kind of thing does that? What kind of thing does this or that? Boom. And so you ask yourself, what kind of thing, when you take the second derivative of it and you add it to the original thing, gives you 0? And the answer is a sine wave. Or a cosine wave. Or e to the I, let's call it t. So if you take the second derivative of e to the it, what you end up getting is a negative e dit. So if you add that to the original, it cancels out. If you take a second derivative of a cosine wave, you get a negative cosine wave. And therefore, if you add it to the original, it cancels out. Same thing with the sine wave. So the only things that can do this are these three guys. And it turns out that all three of them are the same thing. They can be written and related to each other. So this actually is just one solution, one unique solution to this is a sine wave. And it will be of the form, we could write it in a bunch of different forms, but we could write this right here. So we could go x with respect to time is equal to a times sine, and this is a is an arbitrary value that we have to get from boundary conditions, omega t, because we got to remember that omega, oh, I should have written this down. I'm sorry, let me write this out here. That this can also be written as x double dot plus omega n squared x equals 0, because we remember that omega n is equal to the square root of k over m, right? So we'll solve this guy instead of solving this guy and put m in there. And we can have plus b cosine of omega nt, right? So that's one solution to this thing, and I'm running out of room, so I'm going to erase this. Another solution, remember this sine, a cosine wave or a sine wave is just 90 degrees shift of a sine wave. So another solution to this, and I'll just put another letter in there, C, is the cosine of omega nt, whoops, plus a phase shift, right? So these two are equal to each other. They just the different, you'll get a different value for C and you'll get a phase shift, but you can turn the first one into the second one. And the same thing true, and this is a little bit, we don't do this quite as often. We could often say, okay, so I'm just going to use capital D as an arbitrary value of amplitude, and we could say that it's going to be E times I omega n t. And we can show that these are equivalent using an identity, something called the Euler identity. And I think that comes up here on the next page. So I will now go to video 4 of week 1 and see you then.